Good evening, everyone. Myself Nilmoni Karak. So I am a research scholar at IIT Kharagpur, and I am a PMRF NPTEL TA for the course Fourier Analysis and its application by Professor G.K. Srinivasan from Department of Mathematics, IIT Bombay. And this is the last season for this NPTEL course, and today we will see, yeah, actually one more season will be conducted on Tuesday. Okay, this will be extra season. Okay, in that season we will review some overall review for this course. And yeah, so today we'll discuss tempered distribution basically. So last time we have seen the definition of tempered distribution, and this time we will see what is the basic operations for this tempered distribution. And let us first recall the definition of tempered distribution, and we'll see some examples of tempered distributions. Okay, this is your week 12, right? Okay, so one thing we have seen that so the Fourier transform this uh, this is as a linear operator on SR, and is also continuous, right? With respect to the topology of SR. Okay, so now the idea of tempered distribution comes from this. Okay, and by extension the definition, by extending the definition of this and to all LPR. Okay, and so let us recall the definition of tempered distribution. A tempered distribution is a continuous linear map from SR to complex numbers this simple. And the set of all such continuous linear maps denoted by SR. This is simple. So we know what is the dual space of a open vector space, or okay, so this is your, so we consider the linear map, continuous linear map from SR to C. So this dual space is called, the dual space is set of all such continuous linear map. Okay, so the set of all tempered distribution is called as SR. Okay, and this is your space of tempered distribution. So first simple example is your delta naught direct distribution. This is simply from SR to C and given by F to F0 okay, and more generally for any polynomial like qx is any polynomial and f is any element of SR, so f comes from Schwarz function, so also Schwarz space, so f is any Schwarz function, then it is true, right? Qx and fx is SR, because this is trivially SR, so if you multiply with polynomial then this should be in SR. Okay, and if you check this map qx fx dx, this is actually continuous. Okay, so you can check the linearity and as well. Okay, so it defines therefore it defines a tempered distribution. Okay, and more generally the definition was the example was basically so this is to write LP space LPR for p greater equals to 1. So if F belongs to LQR with 1 less equals to Q less equals to infinity, then the map per distribution. Okay, and this was some example. So one interesting we have seen, so this example, more example. So sine e to the power x and cos e to the power x both are tempered distribution. Why? Because so this is easily continuous map, linear map. Also, if you want to do this is basically one. So both are L infinity function, sin e to the power x, cos e to the power x, L infinity r. So they are tempered distribution. But if you do like e to the power x time fx, this is not. So f is any Schwarz function, still this is not, because you cannot bound this by polynomial. Okay, f can be anything, no problem, but e to the power x is there. So the growth is basically always 1 plus x to the power n for any n as extending to infinity. Okay. Now let us see some operations on this tempered distribution. Okay. So one thing, just to recall, if f is in SR, then f dash also in SR, and the map. This is trivial actually. F goes to f dash is continuous. But f should be in ASR. Okay. And now so we studied tempered distribution, but now we want to study differentiating a tempered distribution. So differentiation of a tempered distribution. Differentiating so let u is in S dash r, then define a map SR to C by f dash. So this is like this defines a distribution denoted by u dash known as the derivative of u in the sense of distribution. So one thing we should clarify so u dash, this is the classical derivative of u, and du the distributional derivative. Comparing classical and distributional derivative. So here so you take just in C1, so continuously differentiable means so first derivative is continuous, okay, and vanishes outside minus r for r greater than 0, then this is du minus uf dash, right? And what is this? This is basically okay. This is basically minus r to r. So since u is vanished outside minus r to r, so minus r to r ux f dash x dx, right? And so this is exactly equals to r, so r tending to infinity u dash x fx dx. This is just u f dash equals to u dash f, okay, and this is u dash f. So this du and u dash agree as function SR to C. Okay. Let us see one example. So you can remember Heaviside function h(x). This is basically 1 if x greater than 0, 0 if x less than 0, and this is immediately in L infinity r. So this is tempered distribution. tempered distribution. Okay, so now let us compute the distributional derivative. What is h dash f? So this is minus h f dash, and this is minus, so due to this definition, 0 to infinity hx f dash x dx minus 0 to infinity f dash x dx okay, and this is your f of 0. Because f is in your SR. So this is your delta naught f. So finally what? H dash equals to delta naught. Okay. One simple thing you can see. So okay, delta naught a minute. So this x times any polynomial you can take instead of x to the power n. Delta naught dash equals to delta naught. Okay, how? Because you know uf here, what is this? Delta naught dash xf. This is minus delta naught xf dash. This is minus xf dash 0, and this is basically minus f0. Okay, just derivative with respect to x, and then this is minus delta naught f. So x delta naught dash equals to minus delta naught. Oh, okay, so this ln mod x is tempered distribution. Why? Because this is you can bound 1 plus mod x to the power n as extending to for some n natural number. So this is in so this is tempered distribution. Okay. Now we can see the pairing. Okay. This comes from elementary function analysis. Okay, so the pairing ux of a vector x belongs to V. V is any vector space, okay, and u belongs to V star dual space by ux. So basically we like pair, we do the pairing ux u, like this. So similarly, using this idea, we can like think for any element of any element okay, so an element u belongs to your LP space. The pairing is basically UF, like this. So UF, this is, and UX time f of x dx. So this suggests that distributional pairing is some kind of generalization of an integral. Okay. Now okay, let us recall some interesting thing, that is support of a distribution. Support. Sorry. Okay. So just you Rn to C is a complex valued function. Then the support of U is defined as the this. Okay. So basically this is the smallest closed set outside which the function is identically 0. So what is support of distribution definition? What is the definition now? Let U be a tempered distribution. Then the support of U denoted by U is the complement of the set points P having a NBD NP such that equals to 0 and the complement of the support is an open set. Okay. Some examples. This Heaviside function Hx has support why? Because this is vanished for all so where not equals to 0, this is 0 to infinity, and what is the closure? This is this. Okay. The direct distribution delta naught has support 0. Because this delta naught x not equals to 0 for x equals to 0 only, and the closure is singleton 0 obviously. Okay. Now let us recall Fourier transform of a tempered distribution. So okay, So simple lemma is there first. It's very simple, trivially true. If g hat. Okay. Just using Fubini's theorem one can do this. Okay. Just use the definition. This is what? This is your f at g x x dx. This is your fx g hat x dx. So just use the definition. Start with this LHS and use the definition of f hat. So Fourier transform of f, and you will have double integration. So use the Fubini's theorem to interchange the variables, and then you will have finally you can recover this. Okay. Okay, so now we go to the definition of Fourier transform of temper distribution. So suppose U is a tempered distribution. Then the map G hat, G belongs to SR. This defines again temper distribution. And the star is denoted by U hat, and is called the Fourier transform of U. Okay, let us see some simple examples. So consider first direct distribution, or so this is not the way of writing direct delta. So for belongs to SR, this is delta naught g hat, and this is what, if you multiply, this is g hat and 0, and this is your simply gx dx, and this is your 1g, and just comparing them we will have okay, and using the inversion theorem we would get how for G belongs to SR, and this is what, this is actually your so using the exponential trick we will get this 2 pi g0, and this is nothing but 2 pi delta naught g, so 1 okay. And some theorem are there, so suppose u is in 12, so u is tempered distribution, this means this, right? Then and xu okay. So proof follows routinely using the definition of Fourier transform of a distribution, and okay, I am not going to prove this. next theorem. Suppose okay, U is temper distribution and G is any short function. Then you had a double hat. So delta naught hat was 1. Also, we can study this temper distribution in several variables again. So definition is for SRN, a sequence F nu in SRN converges to F in SRN if for any multi-index alpha 1 dot alpha n and any polynomial qx supremum Rn instead of Rn qx t alpha f nu x minus f of x goes to 0 as Newton infinity. Okay, so the definition is similar, quite similar. Okay. And again, like one variable case, this SRN is complete and SRN is a locally convex TVS, and again the dual space S dash Rn is called the space of temper distribution on Rn, and the Fourier transform of temper distribution in several variables, so is similar, like analogously we can define. And so yeah, basically if u belongs to S dash Rn, then its Fourier transform u hat is defined as G. This is again a temper distribution. G belongs to SR. And again the support of temper distribution in of several variables is defined exactly the same way as in the one variable case. And now now we will see distribution with point support. So this theorem is necessary if U is an S dash Rn has support 0, then U is a linear combination of finitely many derivatives of the direct distribution. That means U is so if support is 0, okay, of course U should be tempered distribution, and this mod alpha less equals to n C alpha delta naught to the power alpha, where delta naught alpha denotes the derivative of delta naught corresponding to multi index alpha. Sorry. On intuition, let D be the closed unit disk x square plus y square less equals to 1, and U be the characteristic function of D, which is a tempered distribution. And what is the so what is the distributional derivative? So so that that is like we would say, so sorry, so if here we want to find the distributional derivative for this characteristic function in two variable. Okay, so you have to find del u del x g and del u del y g. This is basically your del g del x, and this is minus del g del x dx dy. Okay, similarly we can find these, and then by applying Gauss divergence theorem, so we will have the distributional derivative. Okay. Now recall Liebniz theorem from complex analysis that says a entire bounded function is constant. So there is analogous for harmonic function. We now state if U is a tempered distribution on R on Rn, distributions, then U is a polynomial. And additionally if U belongs to LPRN, then U equals to 0 if LP less than infinity. U is constant if P equals to infinity. Okay. Okay, now we will solve some problem related to this, and remaining parts we will discuss on Tuesday, and yeah, something like some differential equation related, continuity of differentiation, okay, continuity of Fourier transform, okay, finally Poisson summation formula. Now let us solve some problems. Okay. Which of the following functions defines a temper distribution? Okay. Okay. So first is your to the power 100x 8x, right? So for one definition, a function fx defines a temper distribution if it has at most growth. For some n so for so this does not hold this, so this is not true. Similarly, this is not true because so and this is your and x cube sin e to the power x. This is polynomially bounded. So here this is true, and e to the power x delta naught. This is what? Let us see. So e to the power x delta naught equals to delta naught, which is in L infinity R. So e to the power x tempered next problem. Suppose f is an entire function such that So what is Liobli theorem? We have just okay. Entire person means here I'm confused little bit. Entire person. So no need to F is enter and F is tempered. Actually F is constant by this theorem. So F of half, so F of 2 half, so not half, 1 by pi, so Fz 1 by pi, double integration, not double integration, okay, actually, yeah, this is tempered. So on R, this f of x is bounded. So this is f of x. So pi into r square, so pi into 100. Answer is 100. Okay. the Fourier transform of the we already have seen just right now. Okay, so 1 hat phi hat. This is actually by calculating the integral to 2550. Okay. Question 4. So hx, this is 1, so support of h and v, support of v should be whole R. This is basically minus infinity to 0 union 0 to infinity, but if you closer, and this is R actually. So now H dash X, so U dash H dash heaviside function derivative this is basically heaviside direct delta. Direct delta and support direct delta is 0 and V dash this is also direct delta. So support U dash equals to support V dash equals to 0. So see, this is 0 infinity, this is R, so this is wrong. And so this is true, this is not true, this is not true. Let's see. So this actually converges uniformly, right? on compact set. So converges in stressor. So this is true actually, but if converges, then its second derivative converges in a stressor. So second derivative means sum k equals to 1 to n k square plus 2 converges. This is not converges as intended in front of this series is divergent, so not true. Sorry, so this is 0. Derivative should be like this. K square is 0. So this is true only, but still this is not convergent. Okay. And for C and D, sum k equals to 1 to n cos kx. I just usually sum this and bound this. Usually this is convergent uniformly on compact set. Also this is convergent in stressor, and this is also kq sin kx. Okay, both are convergent in stressor. Okay, up to this I have prepared, and yeah, so next day means on Tuesday we will see the remaining parts, that is your Poisson summation formula, etc., and we will solve some problems and some applications of Poisson summation formula in different area. Okay, so thank you for attending. I'm ending the session here. Thank you. We will meet on Tuesday for the last session.